Thank you very much, Dave. Appreciate the introduction. All right, my name is Kyle Kingsbury, and we're going to be talking about Jepsen. In this talk, I'm going to be looking at distributed systems, the way they break. We're going to do a little tour of some recent research results. But to start off, I want to give you a bit of context. My name is Kyle. You might know me as Afer online. My pronouns are he, him. And my day job is to break databases. So I focus on the ways in which distributed systems explode under common failure conditions. But before I worked on distributed systems, I was a backend engineer, like I'm sure many of you have been. I built this thing called an API, which is kind of like this illusion, this beautiful rainbow that customers behold. And that rainbow was supported by actual code, here represented by these steel girders, that ran on top of the Ruby runtime, here represented by some wooden pilings. And that wooden piling was firmly planted into a bunch of databases that we found lying around on the internet, here represented by a pile of tires. Now, as anybody who has ever run a database knows, the pile of tires is usually on fire. And it's our job as good engineers to engage in what's called information hiding. We're going to conceal the fact that the pile of tires is on fire. And so while our engineers are screaming and throwing more tires onto the pile in an effort to put out the flames, users will perceive that everything is fine. In short, we're trying to build reliable systems out of unreliable parts. And that's challenging. I'm not just talking about databases here. I also think about queues, discovery services, any sort of coordination primitive. Wherever you have distributed systems, there is fear and terror. Because distributed systems get into split brain, where different sides of the network believe different truths. Or they have broken foreign key constraints, so you can't look up some value that you referenced. Or they have transient anomalies, like you write something and then can't read it back, and later it shows up. Are these just theoretical, or do they happen in real systems? That's the question I've been asking for the last 7 years, and I've been trying to measure real distributed systems to understand what they do in production. I built a library called Jepsen, which is a toolkit for building tests for almost any type of concurrent system. And through Jepsen, we can model the distributed system as if it were one coherent thing. So we have the environment, that's clients, people, the outside world. And the system itself is typically a bunch of Linux processes, some VMs or some physical machines, some sort of networks and disks. All of that we pretend is one thing. After all, that's what distributed systems are, right? It should be one thing. And at the boundary between the environment and the system, there should be some invariants that hold. I should, for example, be able to put something into a queue and then read it back later. If I can't, that would be an invariant violation. So I'm going to run a bunch of clients outside the distributed system. I'm going to know exactly what everyone does, and those clients will interact with different database nodes and hopefully get some sort of picture of what the database does. But notably, we don't have any picture of what's inside the database. We don't do any sort of code analysis. There's no instrumentation, no tracing. This is partly because sometimes the database isn't open source, and sometimes because the language in which it's written wouldn't be amenable to the kind of tracing and proof techniques you might appreciate. So focusing just on the database as an opaque box allows us to write a test which is maximally portable, and yet, hopefully, still finds bugs. So the general approach is to generate some random operation, like set the current value of object X to 3. We make a network request, and we get back a response. And then that response can be interpreted in one of 3 ways. It could be okay, we know it happened. It could fail, and we know it did not happen. Or something else could happen. We could get a timeout or some sort of indeterminate message. And it's important that when this happens, we actually leave the invocation open for all time. That's because the operation may or may not have happened already, and if it hasn't, it could happen later. It might still be in the network, it might be queued, we just don't know. So over time, we're going to build up a concurrent history of operations performed by different clients, some invokes, some completes, some of them crashing and lasting forever. Once we have this history, we could start to ask questions like, is there some sequence of these operations which looks like it made sense? Can we find a path that goes forward in time? That would tell us that the system is real-time coherent. If we have to go backwards in time, we know that it might not be linearizable. The technique I want to talk about in particular today is a cycle finding program called L. This system takes all of those operations and says each one is a transaction, let's find dependencies between those transactions and look for cycles in that graph. Why do we care about cycles? Because cycles tell us when those operations can't possibly have happened in any total order. So if I have two transactions, T1 and T2, and the first one performs a write of some version, call it V1, and the second transaction overwrites that version with V2 of the same object, we're going to call that a write-write dependency. I'll write that as WW in this talk. A write-read dependency is when you write some value and somebody else sees what you wrote. Obviously, the person seeing your effect needs to come second. And a read-write dependency is when you observe something and a second transaction overwrites it with the next version. Now, implicit in all of these definitions is the idea that there is a total order of versions. But when you make queries to a database, you don't necessarily know what the version order is. Like if you ask for the value of object X in the database and you get back 5, and you ask again and you get back 3, which one came first? There's no real way to tell. So the secret in L is to make our data types stronger so that we can introduce some heuristics allowing us to recover the version order. What we're going to do is define our objects not as single values, not as numbers, but as lists. And each list can only be modified by appending a unique object or unique number to the end of it. So if I have the list 1, 2, and I call append x3, the new value of x would be 1, 2, 3. An interesting property of this data type is that if you observe the list 1, 2, 3, you know that the write of 3, the append operation, that had to be the thing that produced that value because it always appends to the end and because every append is unique. The other interesting thing you can do is you can go backwards. If I see the value 1, 2, 3, I can go back to 1, 2. I know that was the previous version. And I can inductively do that process. So if I see version 1, 4, 3, I know that the previous version was 1, 4, before that was 1, and before that was the empty version. So I can infer the total order if I have any visibility at all. I do one read, I get the whole version order out of it, up to that read. This allows me to infer all those dependencies I talked about before. I can see that transaction 1 wrote version 1 of X, and it was overwritten by X2 in T2. I know that that write of 2 to X was visible to a later read of 1, 2. And I know that that read of 1, 2 did not observe an append of 3. So I can extract all three types of transitions, all three types of dependencies between transactions. This allows us to identify a broad swath of anomalies, things like write cycles, aborted reads, intermediate reads, cyclic information flow when two transactions see each other's effects, read skew when you see part of a transaction but not all of it, anti-dependency cycles. We also find some things that aren't in the typical formalisms, like garbage reads, where you read some value that nobody ever wrote, or inconsistencies in the version order when there was no total order of versions itself. We can find internal consistency violations where you have a single transaction which violates its own thread of causality, and duplicate writes when you write something once and it shows up 5 or 6 times. So for one test, ordinarily you would expect to pay a cost of n factorial. That's because it's a combinatorial problem. You have to find every single order of transactions and analyze it. There's a proof that says this has to happen for anything like serializability analysis. But if we constrain ourselves to the particular data types that I talked about, lists with append, we can do this analysis in linear time. And most importantly, we can do it in a way that does not depend on concurrency. That means this process crashes, we don't have to keep stacking up more and more combinations to search. So our general program here is to generate randomized operations, to record a history of those operations as applied to the actual database, and then to verify that history is consistent with some abstract model of the system. And the way that we're going to do that is by looking for these cycles. While this is going on, we're going to call Beyonce and say, please get your network shears. We're going to cut the network into pieces. We're going to change nodes clocks. We're going to kill processes. We're going to pause them. We're going to create chaos and see what happens. Okay. I'm going to talk about 3 databases now, 3 case studies, starting off with Postgres, version 12.3. This is work from earlier in the summer. Postgres, as you may be aware, is a SQL database. And for this talk, we're actually not talking about a distributed system at all. It's just a single node, the simplest possible installation you could do. Now, Postgres offers these standard 4 SQL isolation levels, which means read uncommitted and read committed. In Postgres, both of those are read committed, and that's the default safety level. Repeatable read in Postgres means snapshot isolation. Although this was not written down in the documentation, it was, I think, well known in the community at the time. And then there's serializable, which in Postgres actually means serializable snapshot isolation. It's slightly stronger than serializability, but for all intents and purposes, you could treat them as equivalent. Now I want to focus on one part of this graph. Serializability is stronger then in that it prohibits any histories which would also be illegal under snapshot isolation and repeatable read. But what Postgres calls repeatable read isn't the same thing as like the formalism's repeatable read. So can we see the difference? I don't know. Let's try it out. So let's do a bunch of requests at repeatable read and see what comes out. What we see are transactions like this. This top transaction reads Y and sees the value 1, 2. It must have executed before the second transaction because the second transaction appended 4 to Y. That transaction in turn appended 5 to Y, and that had to happen before the read of 1, 2, 4, 5. But that bottom transaction in turn looked at X and saw 4, 5. That means it had to happen before the first transaction, which appended 8 to X. So we have a cycle here involving 2 read-write edges. That means it's G2 item. This is an anomaly described in Adja and Liskov's formalism for SQL levels. It's illegal under repeatable read, but it is in fact legal under snapshot isolation. So what gives? Postgres claims that repeatable read is stronger than the ANSI SQL repeatable read. Are they wrong about that? Well, it depends. The ANSI SQL standard is actually ambiguous on this point. There are at least 2 possible interpretations of the standard. This actually comes to us from Adja and Liskov, and then Berenson, O'Neill et al. The Berenson paper is notable because it defined snapshot isolation in the literature. And in the paper, they go on to say, look, you could take this interpretation of repeatable read and wind up with histories that are legal, but have weird anomalies. Isn't that interesting? Let's redefine repeatable read to be stronger. So the definitions I'm using come from those papers. They're the broad interpretations of the standard. But what Postgres is doing, and defensively so, is using the strict interpretations which allow these anomalies. That's why this is both legal and illegal under the standard, because the standard is ambiguous. Okay, so enough faffing about with repeatable read. Let's talk about serializability, the property that every transaction takes place in total order, or at least it looks like it. Now, the way that serializability is built in Postgres is by preventing so-called dangerous structures. A dangerous structure is a pair of transactions or a cycle of transactions linked by 2 adjacent read-write edges. Why is this the case? Go read the paper. I don't have a good intuition for it yet. Now, they're going to look for these transactions and prevent them. But when we actually run at serializable, we see some cycles. Like this one, we append Y2, but that had to happen after the empty read of Y in the bottom. And the first transaction observes X to be the empty value, and the bottom transaction appends something to X. So each one of these transactions saw the state before the other transaction's writes. This is an anti-dependency cycle, a G2 item, just like we saw before. And we can find more like this that are indirect. This one has a write-read edge and 2 read-write edges. Now, if you kind of squint and you just draw big circles around those transactions, what you realize is that these are exactly the same shapes of transactions that are supposed to be identified and prevented under serializable snapshot isolation. Isn't that interesting? So it turns out that when Postgres was claiming to be serializable, it was actually not even repeatable read. It was, in fact, strong snapshot isolation, which is snapshot isolation plus the real-time guarantee. You never get to observe values from the past. So that's troubling. It was not as strong as it was supposed to be, and nobody figured this out for a while. This happened under normal operation, no crashes, no problems, just this is what Postgres did. This happened because the conflict detection mechanism inside of Postgres tries to figure out which transactions own which tuples, and it would incorrectly tag a single transaction as the owner of both the old and new versions of some tuple. That meant the transaction would assume nobody had conflicted with it, and it was therefore safe to commit, even if it didn't observe the rights of a prior transaction. Okay, so this was present essentially since the start of Postgres serializability. So every version prior to August of 2020 exhibits this bug as far as we can tell. It is fixed in 9.5.23, 10.14, 11.9, 12.4, and 13. Hooray! What this means is that Postgres, at least my best guess from a little bit of cursory testing, offers strict serializability in recent versions, strong snapshot isolation for repeatable read, and read uncommitted and read committed. The defaults are both read committed. We never saw a violation of those levels. All right, part 2, MongoDB. Version 4.2.6, also in early summer. Mongo and Jepsen, we've got a history. We've done several analyses, some paid, some free. And MongoDB had a web page that talked about all the things that Jepsen had found. And what I thought was interesting was that that page omitted many of the findings from previous Jepsen analyses and instead claimed MongoDB offered among the strongest data consistency, correctness, and safety guarantees of any database available today, which is an awfully strong claim. It also claimed, prominently on the homepage, to offer full ACID transactions, which is a wonderful property that many of us have wanted for some time. Now, when you hear ACID, you're thinking atomic, consistent, isolated, durable. Isolation means that transactions should appear to take effect as if no other transaction were executing concurrently. They should look like they happened in sequence. That means serializability, or stronger. But if you read the documentation, what Mongo actually offered was snapshot isolation. And as we've seen before, not quite the same thing. And this, of course, assumes that you're using majority writes and snapshot reads, which raises the question, well, what are the defaults? And the defaults in MongoDB are that committed writes can be thrown away silently, and reads can show you whatever a node happens to have locally, which could be present, it could be old data that's been overwritten, or it could be garbage data that's going to be disappeared later. You just don't know. So what that means is that MongoDB's defaults are, in fact, read uncommitted. And this is known. This is a result from previous Jepsen analyses. It's been in the documentation for a good 5 years now, so old ground. I want to raise a question here, and I'm not entirely sure about this. Read uncommitted doesn't actually mean everything goes. In the Adja formalism, it prohibits a phenomenon called G0, a write cycle, which is a dependency graph where there are all write edges for a transaction cycle. But that assumes that there is a total order over those committed versions. And MongoDB doesn't actually have necessarily a total order of versions. Mongo is happy to go into split brain and allow two different leaders to have concurrent writes that evolve separately. When that happens, can you compare those values? Do they have an order? I'm not sure they do, in which case maybe MongoDB isn't even read uncommitted. Maybe it's something weaker. I'm not really sure how to evaluate that in this formalism. Okay, so let's try it out. Let's create a collection. We'll ask the database handle from the client to give us read concern linearizable, write concern majority. We're going to issue an update statement on that collection. If you do this, your single document operations will be snapshot isolated and linearizable, at least in the cursory testing I did. This is great. So let's add a transaction. We'll create a session object, and we'll call session with transaction, and we'll change our update operations to use the session. Otherwise, everything's the same. And suddenly, our previously linearizable snapshot isolated history starts showing lost writes and aborted reads. What's going on? This is because transactions actually ignore the database and collection level read concerns and silently downgrade them to local by default. So adding transactions to the system actually makes it worse, unless you make sure to set the read concern snapshot on the transaction options builder. So every time you do a transaction, make sure you are setting that read concern to snapshot if you wanted snapshot reads. And if you do this, you're still going to see split brain and aborted reads. It's not snapshot isolated, which caused me to think for a moment I'd found something very interesting. And then I discovered this is actually also in the documentation. Snapshot read concern only gives you snapshot isolated reads if you also use write concern majority. And this doesn't just apply to read-write transactions, it also applies to read-only transactions. So even if you're doing no writes, you can see histories like this one. You read X a bunch of times and see it go empty 1.5, 1.5.6, and then all of that data disappears and you get empty 3.3.7 as if 1.5.6 had never happened in the first place. So when you do a request, you need to call read concern snapshot, write concern majority, even if you're only doing a read. This is in the documentation. It's just surprising, that's all. Now, maybe the question is, how many users are bothering to do this correctly? MongoDB's research suggests that 80% of users of their hosted service use the default write concern, and 99.6% of users use the default read concern, which means that these people are, whether they intend to or not, getting unsafe default behavior. Hopefully the idea is that it just happens infrequently enough that it doesn't matter for their applications. And this could be a valid assumption. The paper goes on to argue that. Now, you might ask whether MongoDB's documentation showed examples of correct usage, and the answer is not really. They used read concern local and write-only transactions, or they used only the defaults. There were actually no examples I could find of doing snapshot-isolated reads. So I went looking for third-party blog posts, and of the dozen or so I evaluated, almost all of them claimed snapshot isolation or ACID, but they either used the defaults, which, as we've seen, are not snapshot isolated, or they explicitly set weaker options. There were only a couple of blog posts I found that knew how to do this correctly. So I think the MongoDB community has some careful reading to do. Make sure you read this documentation to figure out how to use transactions correctly. Now, as we've pointed out before, snapshot isolation isn't necessarily the same thing as ACID. Here is a G2 item, a write skew, just like we saw in Postgres. One transaction reads the empty value of Y, and T2 adds something to Y. So T1 has to come first. But T2 reads the empty value of X, and T1 appends something to X. So T2 had to happen first. Clearly, these things aren't isolated because they executed mixed into each other. But this is still legal under snapshot isolation. This leads to this weird phenomenon where you can find clusters of 123 different transactions, all of which executed both before and after, i.e. during, other transactions and observe their effects mixed together. But this is still, according to the MongoDB marketing, fully ACID. What does ACID even mean if not fully isolated? I don't know. Now, is this common? It depends. In the transactions I was generating, which were intentionally designed to create conflicts, about 10% of transactions violated isolation in healthy Mongo clusters. Again, this is still snapshot isolated. It's just not serializable. Does it actually matter for your application? Maybe. Many applications are perfectly fine under snapshot, or even weaker, but you're going to have to look at your transactions to figure out whether that holds or not. Okay, so let's try it again. Let's try majority and snapshot and see what happens. What you'll find, at least on MongoDB 4.2.6, is that you can append a value to an object, like append 6 to X, and then go to read X and see 6876. It's as if the write took place twice. Then you start to think, maybe there's like a transaction retry mechanism that improperly retried the transaction. And you go to turn it off, and you find out that the transaction system ignores the retry write setting, so you can't disable it. Okay, you go on to find more cycles. Here's one where the first transaction adds 4 to Y, second one adds 5 to Y, and we have a later read that shows 4 comes before 5. It's a right edge. The second transaction reads X12, and the third transaction adds 3 to that, so the third transaction happened later. And the third transaction's append of 3 to X is visible to the first transaction's read of X. So we have a cycle with only one read-write edge. This is new. This is interesting. This is called G-single. It's a read skew, and it's illegal under snapshot isolation. It gets worse. We can see transactions where both observe the other's writes. So here, both transactions appended to some key, and then the other one saw that append. That's G1C, cyclic information flow, and that's prohibited under not just snapshot isolation, but that's illegal under read committed. And in fact, we can even see single transactions where you read X 1, 2, 3, 4, but that write of 1 is one that you executed later in the same transaction. It's as if the read had time traveled forward in time to read your effects from the future. And in fact, there's also a bunch of other write edges here. Other transactions added X2, X3, X4, and all of those are visible. All of this points to a retry problem. We found internal consistency violations. So for MongoDB claimed to be ACID and the documentation claimed to be snapshot isolated, it was actually something, I think, weaker than read uncommitted. This is probably due to server 48307. Committed transactions could incorrectly appear to fail, and the retry mechanism would retry them when it wasn't supposed to. That was fixed in 428, and I've done a couple hours of really quickly looking at 428. I haven't seen a violation since. So fingers crossed, Mongo offers snapshot isolation as its strongest isolation level, but you need to be aware that the defaults are read committed or maybe something weaker. Last but not least, I want to talk about Redis, and in particular, Redis Raft. Redis Raft is a replication system for Redis. It's got many ways of replicating, and this is a new one from Redis Labs, which is based on the Raft consensus algorithm. All of this research is based on unreleased internal builds, so there are no users to speak of. Now, in theory, using Raft should give you linearizability, or at least sequential consistency. And linearizability over multiple transactions, that's strict serializability. To put this into normal person terms, every operation, every transaction should appear to happen in some total order, and that order needs to be consistent with the real-time order you observed them. So if you write X, you should be able to read that write later in real time. The first thing we found was that Redis would go into infinite loops. You'd issue a set request to a follower, and with proxying enabled, the follower would send that request to the leader. The leader would broadcast the request, get acknowledgement for the set, and commit it. And the follower would say, great, what do I do with a set operation? Oh, I'm a follower, I'll proxy it to leader. And the cycle would repeat again. So it would sit there thrashing itself endlessly until it ran out of memory or disk. That was fixed by adding a reentrancy check. But it turned out that there was a related bug. We'd see on any failover event, all of the data in the cluster disappeared. This happened because with proxy mode disabled, a leader would get a set request, broadcast it, commit it, and the follower would say, what do I do with the set? I am but a humble follower. I'm not supposed to execute any operations. I will throw this in the trash. So as a result, only the leader had any state. The followers didn't have anything in their state machine. That was fixed by the same reentrancy check. We found split brain and lost updates related to the joint consensus mechanism used on membership changes. When you change memberships, you're supposed to get approval from the old group of nodes and the new group of nodes before you can move on. But in Redis Raft, you could tell a node that it was the only person in the cluster. Like, forget about your old friends. And that node would then go on to believe itself the leader of a single node cluster and execute all the writes it wanted in isolation. Of course, this led to lost updates. This is because the Raft log type remove node message was left out of the set of message types that was supposed to be considered a configuration change. So it just needed to make sure to look at that message properly. This was fixed in 8.8.EA7. We found issues with transient stale reads. You'd write something to the database, and then you go to read it, it would show up. And then if you restarted the node, it would disappear. For a little bit, you'd see like the empty state. Or you'd be writing things along happily, and then with no apparent cause, you just observe something from 5 seconds ago. This happened because the Raft library didn't issue a no-op log entry when a new leader was elected. That's part of the specification in the Raft algorithm, but not every implementation does it. This was already fixed upstream, so they just had to merge the changes. We found issues with availability as well. Nodes would shout that there was no leader in the cluster for hundreds of seconds. So you'd be running along, doing operations, everything's great, no faults required, and then it would just fall over saying, no leader, no leader. This happened because of a number of bugs, mostly involving connection handling issues that caused the state machine to stall for a long time on an election. And the election timeouts caused it to happen often because the timeouts were set fairly aggressively. That was fixed in recent builds. We found aborted reads, again with no leader. You'd issue a write and it would say, oh, there's no leader, I didn't do that write. Or so you would think. But then you go to read it and it turned out that your write did complete after all. This was addressed by a whole suite of protocol level fixes. We found that you could do a transaction, abort it, or discard the transaction state, and it wouldn't necessarily discard. Sometimes those operations would get squirreled away in some weird place and show up later. This happened when you do like a multi-operation, start a transaction. You would issue a couple of requests, and you say exec to commit. If this fails, you would say, okay, great, discard the connection state, start fresh. But what would happen is the set and push operations would get saved for later. And if you later issued a new transaction, like get X, your earlier set and rpush operations would get pulled into it and executed first. This happened because the discard operation went through the raft log directly. So every single thing you did in the transaction, it was a separate log entry. If your discard failed because of a timeout or something, you'd end up with all of those operations still in the state machine, still in the raft log, and they would get folded into the next exec. This was fixed by adding a local state machine that buffers the operations first. We found crossed wires, and this is one of my all-time favorite bugs. You'd issue a request, and if there were network partitions and crashes involved, Redis Raft could send you back a response intended for someone else. And if you're lucky, this is a type error. But if you're unlucky, you get a type that's the same as you expected, and you just get silent data corruption. Like you asked for the number of days that this restaurant has been open, and you got back the age of the Grand Canyon in millennia. So this happened because the response logic used the wrong context object. There were a Redis Raft context and a request context, and they just typoed the wrong context. There were a few other issues here as well, but we got fixed. We found more cases of split brain, more lost updates. You could have membership changes and crashes result in states where the middle of a history would diverge and then come back together. So you'd see like 125 on one node and 1345 on another. This was a bug in the underlying Raft library. Nodes were supposed to be demoted before removal, but they were instead left running and could still participate with their data files even after being removed. This is fixed as well. We found more transient empty reads. This is a litany. I'm going on forever, but nodes which restarted after membership changes could temporarily exhibit empty reads. We could have a bug in the log loading process where you would look at the log, try to replay to figure out who owned what when, and use a set of all nodes rather than a set of voting nodes to figure out if someone was committed. You could also treat former members of the cluster as if they were still alive, send them messages, and get confirmation. So that was fixed, and we found more cases of split brain. We'd find divergence at the tails of histories where a single list would go into two different versions of two different nodes due to a bug in the snapshot process. Snapshots would be fine in memory, but due to a bug in the way they were written to disk, you'd end up with state that couldn't be recovered properly. There'd be nodes missing from the snapshot on disk. That was fixed, and we found dueling histories, another case of split brain. This is uncommon for Raft systems, but I think this is because this system had never been deployed before, hadn't really had a chance to go through shakedown, early prototype, and also because the underlying Raft library just hadn't had a chance to be used in this kind of context before. That happened with process kills, fixed as well. We found a whole bunch of crashes, seg faults, invariant violations, you name it. Those were not really safety related, but they did cause issues with availability. All fixed now. So Redis Raft's goal is to get strict serializability, but it was actually something weaker than read uncommitted. It allowed all kinds of terrible things to happen. However, all of this stuff was in early development builds, so no users were actually affected. This is precisely the stage at which we want to find awful bugs. My guess is that by the time Redis Raft gets released officially, they will have had lots of time to shake this out, and towards the end of our testing, we were seeing what looked pretty close to strict serializability in all of our runs. So I'm optimistic. To recap, when you choose a database, whether you choose a commercial one or an open source database, you're essentially signing a contract with the vendor. And the vendor, here represented by Ursula the Sea Witch, may have hidden some terms in that contract which you might want to be aware of. If you don't kiss the prince by the third day, your data might be forfeit. So read the documentation very carefully. Look for consistency models. Look for failure modes. Try to figure out what happens when nodes crash or are partitioned. Then test it for yourself, because oftentimes the documentation lies. Look out for words like strict consistency, acid, strong. These are words which don't have a super well-defined meaning, and vendors are therefore free to use them in ways that might be surprising. So when you do see something like acid, or you do see strong consistency, try to ask what else is this coupled with? It can be sensible in context, but you want to see an actual model like serializable or linearizable to go with that. I want to encourage both vendors and users to be formal and specific in the consistency models and safety properties they expect and provide. And also to acknowledge that not everybody needs this safety. For all those Mongo users running it like read uncommitted, is that bad? I mean, lots of companies are still doing okay, right? So maybe this isn't the end of the world. There are many applications in which data loss is actually fine. I harp on this often, to use proven algorithms. I'm always telling vendors, don't invent your own. But as we've seen with both Postgres and Redis Raft, proofs aren't enough. You can wind up with a system that breaks either because the implementation of the proof isn't correct, or oftentimes it's the coupling of the implementation to some other system. Like the snapshot system in Redis Raft, the logging of the snapshots is kind of out of scope of the core replication system, but it could still lead to consistency anomalies. When you do testing for these systems, consider your failure modes. Inject things like process crashes with kill-9. Try killing nodes by pulling out their power switches or by running AWS terminate. Try inducing clock skew with date or libfake-time. You can simulate garbage collection I/O pauses with sigstop and sigcontinue. And you can simulate network partitions, which I think are one of the most useful tools for inducing distributed systems faults with iptable-j drop. A little bit of TC, the traffic control program, will get you simulated latency. And that can be helpful for testing any sort of system which has performance constraints or is intended to be geographically replicated. What I'm advocating for is property-based testing. Instead of writing down the specific sequence of operations you want to perform, generate randomized operations and then apply them to the system. This was successful because we're able to create we're able to create transactions which nobody had thought to ask about. Postgres had an extensive test suite for serializability, and it passed that test suite for years. But nobody had thought to write the particular extremely strange combination of operations that Jepsen made up by random. So try property-based testing. When you do this, think of high-level invariance. The more general your program verification, the better. That's why L has been so successful, because it can verify all kinds of properties at a high level. But you don't have to use something complicated to get good results. If you're building a user registration system, maybe your invariants are things like, after changing a password, the user can log in using that password. Maybe your verification is, you can only register a user account once. These are simple invariants that you could apply to your own services. And when you do this testing, it's not enough to do it in the happy case. As we saw with Redis Raft, inducing failure modes, like a failover, can make the system do something very surprising indeed. So try a little bit of that. Finally, if you look for perfection, you will never be content. Every database has problems. Running databases is an almost impossible problem in itself. So I want to have a little bit of humility and respect for the people who are trying to make these things work. We should understand that they're going to mess up sometimes. That said, doing a little bit of testing, a little bit of experimentation up front can yield dramatic results. And that's what I'm hoping you'll take today. This work would not have been possible without my research collaborator, Peter Alvaro from UC Santa Cruz, Kit Patella, who helped write early versions of L and has made many contributions to Jepsen, Andres, Peter, Felix, Thomas, and Daniel from the Postgres team, Maxime from MongoDB, Redis Labs, who funded their analysis, specifically Yiftach and Yossi from Redis. Thank you all very much for coming to this talk, even virtually. It's nice to see all of you. I'll be in the Slack to take questions later. And if you want to read about any of this research, you can go to jepsen.io. Thanks.